Okay, I welcome you all. We are back in the classroom situation, and I thank you all to be present in this class right now. And in this class, we have a course on quantum mechanics, and we will have to go through that course. But since this is the first class of this class, I thought let us revive our past. Let us see what has happened in the past and where we are moving now. And obviously, again, I have something in my mind that I want to share with you. Before we go with this introduction, where we will take into account the different things that have happened till now. And the point is that we have two basic frameworks in physics. One is classical, another is quantum mechanical. And you have mathematical framework, as in case of classical, you have classical physics, you have mathematical physics, you have statistical physics, you have classical statistical physics, you have quantum statistical physics. But at the top, we have two dimensions, we have two frameworks. And let me be clear at this point of time that both of these theories are not complete. They cannot completely define the nature of reality. As you find the drawbacks in the classical physics, you will also find drawbacks in quantum physics. But let me tell you frankly, quantum mechanical physics is more fundamental than that of classical physics. Or I should rather say that there happens to have cases where we understand that classical physics is an approximation of quantum physics. Now again, I want to take you back to a story. And this story may take us into the framework of the course that we are discussing. Now, if you imagine that there is a scientist I'm putting here because I assume that this person can measure. He can measure. He has a capacity to measure. And this man is standing on a hill. And if we assume that this hill is at the mid of an ocean, and this hill is surrounded by water, the man standing on the hill can see a flash of light. Assuming there is a ship, there is only one ship in the ocean. The ship is not visible to the person standing on the top of the hill, but he can see the flashes of light. And he can observe the motion of the flashes of light. What is coming to him? Light, electromagnetic radiations. He can accurately predict that there is something in the ocean. Right? He can predict, not only predict, he can calculate that there is something in the ocean and this something is moving with this speed. He can completely measure that this object, with respect to his cliff on which he is standing, it started from A and it has reached B. This person can calculate and observe and predict everything about the flashes of light that are coming out of that ship. This is classical physics. This is how we discuss. This is what makes a background of classical physics. But now imagine the same experiment, the same person on the top of the cliff. But now the light that is coming from is very, very small. Now this ship, the size of this ship is equivalent to the size of an atom or equivalent to the size of a molecule. And the flashes of light are coming from it. Atom can make the transitions, you can have the radiations. If an atom is in an excited state, it will emit the radiations. Now you have a person standing on the cliff and trying to measure, trying to observe. In the previous case, he was pure about it. He was sure about it, that there's a ship. And he was sure that there's only one ship. He was very much sure about that. But now, the ship is converting into a very, very small dimension. The dimension equivalent to the dimension of an atom or the dimension of a molecule. Now he is looking, he is measuring. What will he see? What will be his observations? His observations will be very strange. He will observe two ships at the same point of time. He will observe 10 ships at the same point of time. He will again see, there is no ship at all. In the previous case, he was accurately predicting. He was accurately observing. He could exactly tell you that there is one ship. But when the size of the ship is equivalent to the size of an atom or molecule, the light is coming from the ship. When he is looking at the ship, every observation is giving a different result to him. Now his observation is not certain. His observation is not accurate. Don't say accurate. His observation is giving the results that are strange. He can see 2 ships. He can see 10 ships. He can see 100 ships. He can see no ship, because now he is seeing the probabilities. He is not observing the certainties that we have in the framework of classical physics. He is seeing probabilities. Now what he is seeing is quantum mechanics. What he was seeing when it was a big ship was classical mechanics. So there is a race going on. It's moving from classical physics to quantum physics. Because, let me tell you frankly, it was believed up to 19th century that physics is complete. In fact, the statements came through the scientists. I think Clausius was one of the scientists. He told us that if you can measure anything up to sixth decimal place, you can accurately predict the nature of that reality. Physics seemed to be complete. everything was framed. Come on, it's done now. We can do everything. We can measure everything. But this is how I would like to move on. Let's see how our slides tell us, and let's go with that. Okay? So, I don't know how to move it. So what we have, look into the early 20th century, when the classical physics began to break down and quantum ideas emerged. So up to 20th century, what it was believed, it's over. We have done it. We can calculate. Everything we can calculate. Provided you can measure it up to the 6th place of decimals. Now this is the way I have to move on. Now, see a time when people say, come on, it's done. We know the nature of reality. But now there is appearance of crisis. There is crisis in the world of science. And science appeared complete. Physics appeared complete. You could measure it. You can talk about the realities completely. You can predict future of any object, provided you know the initial conditions of that object. You can predict each and everything about that. But the experiments that were conducted, one of them was black body radiation, stability of atom, photoelectric effect. All of these experiments, they challenged the nature of reality. Talking about photoelectric effect, because it was a time when light was assumed to be an electromagnetic wave. It failed to account for the photoelectric effect. Why do you have emission of electrons from the photosensitive metal, provided the frequency of the light is greater than that of some minimum frequency, what's called as threshold frequency. Assuming that light is a wave, it is impossible for the electron to leave the surface of the metal. So it's a big problem coming around. You cannot explain it. And you are saying that the physics is complete. Black body radiation. What's a black body? If you choose an ideal black body, it absorbs all wavelengths and it emits all wavelengths. Classical physics could explain this. Do you remember that curve? It could explain this curve in extreme regions. Wein's law could explain in the lower wavelengths. Rayleigh-Jean's law could explain in large wavelengths. In fact, you have ultraviolet catastrophe. But experimentally, what you are seeing the curve like this. You have a maxima, then there is going down. And you are trying to explain this process using the old mechanics, in which everything was believed to be mechanical. The results that you see as a physical reality is mechanical. Atomic stability. Electron revolving around the nucleus. Electron is a charge. And the classical physics telling us, if you have a charge and it has an acceleration, it will emit electromagnetic radiations. So if electron is revolving around the nucleus, at every point, the velocity of the electron is changing because the direction of the electron is changing. So if the velocity of the electron is changing, it's accelerating. So if it's accelerating, it should lose electromagnetic radiation and it should fall into the nucleus. So this is why I call it crisis. It was a crisis of classical physics. Clear? So now comes Max Planck. And what he does, he introduces the idea of packets of energy. He says, come on, it doesn't work that if light is an electromagnetic wave. It does not explain the problem of black body radiation. He comes up with an argument that energy is quantized. to explain the black body radiation. And we have seen it in our previous classes, how it explains purely that you have a curve that you find in the laboratory. So Planck was able to resolve it. He resolved the ultraviolet catastrophe problem, as I said. Because what is ultraviolet catastrophe? For infinite frequencies, infinite energy. That's what's called ultraviolet catastrophe. But that's not the case. Your curve is going up and then it's coming down. So Planck resolved this ultraviolet catastrophe by assuming energy is emitted in discrete quantas. It was a very working argument. And still it was that time when the person like Albert Einstein, he failed to accept that quantum mechanics is something more fundamental than that of classical physics. So, you have a constant, a fundamental constant, Planck's constant, that defines the size of this energy quantum, isn't it? Because E is equal to h nu. The packet of energy is a multiple of this Planck's constant. And you see its value is very, very small. And then comes photoelectric effect. As I said, Einstein was not in favor of something spectacular that was happening in quantum mechanics. You might have heard a word, quantum entanglement. What is entanglement? If you have two particles, they interact. Okay? If they interact quantum mechanically, you take one particle at the edge of the universe and take another particle at the edge of another edge of the universe. The entanglement tells us that if you disturb the particle at one edge, you will see the result at another edge of the universe. That means if you disturb the particle at A, which is, say for example, at the edge of the universe, if you measure, suppose you measure the spin of this particle at one edge, suppose it comes up, you will automatically know that the spin of the particle on the other edge of the universe is spin down. So what does it mean? It means there is some kind of interaction. But see, this argument is very, very complicated argument. This is what Einstein called spooky action. He said, come on, what are you talking nonsense? How is it possible that you can influence a particle on the edge of the universe when the other particle is at the another edge of the universe? Even he wrote down a paper against it. That paper is known as EPR paper. Einstein, Podolsky and Rosenberg. They tried to explain in that entanglement should not be the reality. And the same person got Nobel Prize in quantum mechanics, because photoelectric effect is quantum mechanical in nature, right? So Einstein used the Planck's idea to explain how light knocks electrons off metal surface. We understand if you have discussed it. So light behaves as both particle and a wave. Photons carry energy in the discrete pockets. Atomic models before the Bohr, Thomson-Pudding model, and Rutherford's nuclear atom, they set the stage. As I said, electron revolving around the nucleus should emit electromagnetic radiations. It should not exist. The atom should not exist. But the reality is that it is existing. We are observing it in our laboratories. But the theory is failing to explain the stability of the atom. If you think about that Rutherford gold foil experiment, what was it? I want your arguments. You have a gold foil You bombard alpha particles, and you see the greatness of the man, that he is able to see the deviations, 1 in 10 to the power of 8 interactions. How many times, how strongly he has peeped his eyes into the experiment. So what he finds? He finds atom is empty. 99.9% of atom is empty. And he is able to discover the nucleus of an atom. Even though, that's why sometimes Rutherford is also known as the lord of the nuclear physics. Because he was the person who discovered the nucleus. So what he revealed, the existence of small, dense and positively charged nucleus. This is what was his experimental outcome. So Niels Bohr's quantum atom. So Bohr applied quantum ideas to Rutherford's model to explain the atomic stability. Now you see, what was his idea? It was a complete argument. It was a postulate. But this postulate worked. Quantization of angular momentum. Electron is revolving in those shells which are non-radiating. See, he is not telling you how, he is not telling you why, but the argument this man is giving is consistent with the laboratory experiment. When you do the experiment, you see, you observe the quantized energy levels, right? So, Bohr could go on. Electrons orbit in fixed energy levels without radiating energy. Now, who will explain this to me? Is there any explanation for this? No, there is no explanation for this. Okay, so it's a postulate. Without radiating energy, energy is emitted or absorbed during these transitions. Okay, it absorbs a quanta of energy, then it goes into the higher energy state, and the reverse. And the next thing, as I said, he comes up with a postulate that the orbital angular momentum of the electron is quantized. And this orbital angular momentum of electron is an integral multiple of that thing, that small constant. It's an integral multiple of h cross. Now it's a success. It's the success story of the Bohr. Bohr successfully explained why you have the things that you observe in the laboratory, why atoms exist, why atom is stable. At least he's able to peep in that. Okay. Give me a minute, okay? Okay, I'll just sign this document. Yeah. Come on, you can also fall into the discussion. Come on. Yeah. So you have a success story of Niels Bohr, okay? It failed to talk about the multi-electron atoms. It could not explain the fine structure of hydrogen atom. And there were other corrections that were incorporated. Sommerfeld theory was one, and it was introduced that it was assumed that, come on, these orbits in which electrons are roaming around the nucleus, they are elliptical in geometry, and there are some relativistic corrections for the better accuracy. Like, because you see, if you go into the framework of spatial theory of relativity, what happens there? If you have an object moving with the speed close to the speed of light, you have a different physics now, right? Because you have the phenomenon like time dilation right? So you have those phenomena. So when you take into account the Bohr model of a hydrogen atom, you don't take into account the relativistic effects. Okay, you choose it as if you are working in non-relativistic framework. So that's why if you want the better results, you have to take into account the relativistic corrections. Now this whole story that I was telling you, this goes with old, you call it old quantum mechanics. The quantum mechanics that was developed by Bohr, that was developed by Albert Einstein, right? Even Rutherford had his role in it. Even Rutherford had its role in it. So this old quantum theory, it's a semi-classical approach. Okay, it's a quasi-classical approach, combining the classical mechanics with the quantum rules. Okay, that's not something that you are going to discuss. I mean, this class is, it will work out as a foundation of a quantum mechanics. You will have to go through the foundational course on quantum mechanics. But here I am trying to introduce you with the problem. So what you have this old quantum theory, and you have Bohr's correspondence principle. Classical physics should emerge from quantum theory at large quantum numbers. Okay, this is also called as quasi-classical case. You will discuss this in semester 2 when you will go in quantum second. So now this old quantum theory, it has built a stage. It has built the base of the house of quantum mechanics. Set the stage for modern quantum mechanics that is developed by Schrödinger, Heisenberg, and Paul Dirac. So they gave us a complete formalism. A formalism that from which you automatically lead out to the quantization of angular momentum of hydrogen atom. You automatically come out to the principal quantum numbers. So all the quantum theory was replaced by the fully mathematical quantum mechanical framework. So all of those things that you have, they fall in the framework of all the quantum mechanics. Bohr model, okay? So they fall in the framework of all quantum mechanics, but what we have to discuss is the quantum mechanics that was formally introduced by Paul Dirac, Schrödinger, Heisenberg, Pauli. They were the people who developed a complete framework of this quantum mechanics. So from Planck to Bohr, early quantum ideas revolutionized physics and laid the groundwork for the modern science. So your semester will all go through this framework that was developed by Schrödinger, that was developed by Dirac, that was developed by Heisenberg. And we will be starting with the basic postulates of this formalism. Any questions? Yes?
Is there any possibility it will overframe or something other than methodology?
Absolutely, absolutely, yeah. The pages are open. Anybody can come up with a new mathematical model, or maybe something new. So suppose we have string theory. In string theory, you have a different class of numbers. Okay, that's a completely different framework. So you can come up with the theory, but what is important for the theory is that it should be consistent with the experiments. If you cannot test it, then it remains a theory. Okay, so if something is testable, then certainly you are moving towards an answer. But answer, you will never find an absolute answer in physics. No doubt, stage 1, I will go with it, I will find an answer, but this answer will raise another big question. Then you will try to look for another answer. You will get that answer. Once you solve that problem, you will come up with another question. This is how nature works. This is how complicated the nature is. Will you please stop it now? Or should you come on?